In the first question of this paper, we are presented with a hot air balloon, a slowly rising hot air balloon, and we're given its velocity as a function of time. And we're asked to determine the acceleration of the balloon at t is equal to 8 seconds. Now, if we're asked to find an acceleration, and we're given a velocity, we have to remember acceleration is the rate of change of velocity. That's what acceleration is. So to find the rate of change of something using calculus methods, then we differentiate that function. Now, if we differentiate the function and we insert an 8, we get an answer of 1 meter per second. And you can actually see the graph of the function that's been drawn, and you can see the tangent of the line at t is equal to 8 seconds. The gradient of that line is the rate of change of the function at that point, which of course is the acceleration. So now we're asked to work out the vertical displacement of the balloon after 8 seconds. Now recall, displacement is the product of velocity times time. So we're not differentiating here, we're integrating, because this is a product we're speaking about. So we integrate our velocity as a function of time with respect to time from 0 to 8 seconds, and you get an answer of 6.6 meters. And that 6.6 meters is represented by the area under the velocity time graph. So that was quite a straightforward wee question to start us off, and it illustrates the power of calculus when it comes to solving problems in mechanics and physics. The only problem here that I would see, now you ought to be well prepared for this question. The only problem I can see is making a mistake. But take your time and it should be okay. Question 2 is a question on rotational mechanics. We have a microwave plate making 6.2 turns or 6.2 revolutions in 60 seconds. Now recall, angular velocity is angular displacement in radians divided by the time it took that angular displacement to take place in seconds. You should also know that when the plate makes one complete revolution, that corresponds to an angular displacement of 2 pi radians. So if it's making 6.2 revolutions, that will correspond to an angular displacement of 6.2 times 2, which is 12.4 radians. Divide that by 60 seconds and you get an answer of 0.65 radian per second. Now, in question 2b part 1, we're asked to work out the unbalanced force acting on a P that's going round with the plate. We'll put a P at 83 millimeters from the centre of the plate, and recall, anything that's going round in a circle has to have an unbalanced force acting on it that we call the centripetal force. The centripetal force in this case is due to the force of friction between the P and the plate, and that's the only force acting in this case. So, what's the value of that centripetal force or unbalanced force? Well, we've got a couple of choices. We can use F is equal to mv squared over r, or mr omega squared. Both are equivalent. But we know what omega is, so we're as well using that one. Put our values in. Remember, 0.36 grams is 0.36 times 10 to the minus 3 kilograms, etc. And we get an answer of 1.3 times 10 to the minus 5 newtons. And that force is always acting towards the centre of the plate as it goes round. Now we'll put on an identical P further out from the centre from our initial one at 120 millimeters, and we're asked why is that one unlikely to follow a circular path. Well, let's look at the formula F is equal to mr omega squared. The masses are the same, they're identical P's. The omegas are also the same because they're making a complete revolution in the exact same time. So the omegas are the same. What is changing is r, the distance the P is from the centre. As that gets greater and greater and greater, the centripetal force required to keep it in a circle also gets greater and greater and greater. In fact, if you double the distance from the centre, you will double the centripetal force required to keep it in that circle. The centripetal force required, remember, is provided by the force of friction between the plate and the P. There will become a limit to put that friction, there will be a limit to that frictional force, and when that limit is exceeded, the P will come off. Question 3, part A. Now this is a question in rotational dynamics, and we're asked to calculate the moment of inertia of a solid body. So what is this mysterious property of bodies called its moment of inertia? Well, let's look at the situation in linear dynamics, where we didn't discuss moments of inertia, but we did discuss its equivalent, mass. What does mass mean in a dynamical sense in physics? Well, suppose we have got this body and we apply an unbalanced force to this body, and the body has an acceleration. We find that the acceleration of the body is inversely proportional to the mass of that body. Therefore, the greater the mass of the body, the less the acceleration, and vice versa. In rotational dynamics, well, the situation is this. We've got another body, and we apply an unbalanced torque to that body, and we measure its angular acceleration, and we find that the angular acceleration of the body is inversely proportional to the body's moment of inertia. Therefore, the greater the moment of inertia, the less its angular acceleration will be for a given torque, and vice versa. So inertia simply means resistance to changes in motion, whether it's linear motion or rotational motion. It's the exact same thing. Now we're asked to work out the moment of inertia of our solid uniform disk. Now usually, to give you the bigger picture here, what we normally have to do when we work out the moment of inertia of a body, we need to take the body into the lab. We apply an unbalanced torque to that body. We measure the body's angular acceleration, and we divide the unbalanced torque by the angular acceleration, and that gives you the moment of inertia of that body. And that's what we normally have to do. But in this case, we've got a perfectly symmetrical body. It is a uniform, solid disk. So we can use calculus methods to work out the formula for that body. And you can actually see from the table of other uniform symmetrical bodies, we have got a formula of 1/2 mr squared for a solid uniform disk. So we don't need to take it into the lab. We don't need to measure, we don't need to apply unbalanced torques and measure accelerations. We can do it a lot quicker now if it's a perfectly symmetrical body. All we need to know is its mass, which we do know is 0.82 kilograms. We need to know its radius, and we do know that it's 150 times 10 to the minus 3 meters. So if we put that into our formula 1/2 mr squared, we get an answer of 9.2 times 10 to the minus 3 kilogram meter squared. And that's what we're required to get. So we've taken our solid disk, put it onto an air-bearing turntable to reduce friction, giving it a wee torque, and it starts to go around with an angular velocity of 12 rad per second. We then come along and very gently put on a ring. The ring has got a mass of 75 times 10 to the minus 3 kilograms, and it's got a radius of 130 times 10 to the minus 3 meters, and we put that on top so the centre of the ring matches the centre of the disc. But then notice its angular velocity changes, and we are asked to work out the new angular velocity using the principle of conservation of momentum. I should say the conservation of angular momentum. Now, the conservation of angular momentum states that in the absence of external torques, and we can assume that, the angular momentum before the coupling will be equal to the angular momentum after the coupling. But it's mathematically stated then that I subscript B, omega subscript B, is equal to I subscript A times omega subscript A, where the A represents after the coupling and the B represents before the coupling. We then put our values in, but we have to remember though, the moment of inertia after the coupling is different from the moment of inertia before the coupling. Before the coupling it was simply the moment of inertia of a solid disc. Now we've got a solid disc plus a ring. Now, the moment of inertia of a ring is exactly the same as the moment of inertia of a particle or a mass going round and round and round with the same radius and the same mass. That's simply mr squared. So when we put everything into the formula, we see we get a reduced angular velocity after collision of 11 rad per second. So it's went down from 12 rad per second to 11 rad per second when you added the ring on top. So we've increased the moment of inertia of the system, therefore its angular velocity has fallen from 12 to 11. It's lost 1 rad per second. Question 3b, part 2. We're asked to find out the loss in rotational kinetic energy. Given the angular velocity has went down from 12 to 11, work out the loss in rotational kinetic energy of the system. Well, that's a straightforward question. All you have to do is find the formula for rotational kinetic energy, and that's given. It's a half I omega squared. Evaluate that with the values before the collision, the coupling, and evaluate it with the values after the coupling, and subtract the answer after from the answer before to get an answer of 0.03 joules. Question 4a. We're asked to find the potential at a point above the surface of Mars. For that we have a formula. V is equal to negative gm divided by r, where g is the gravitational constant, m is the mass of the planet, and r is the distance from the centre of the planet to the point in space in question. And that's the distance of the radius of Mars, 3.39 to 10 to the 5 10 to the 6 metres, plus the height above Mars, 2.5 times 10 to the 5 metres. Put that into the formula and we get negative 1.18 times 10 to the 7 joules per kilogram. Now you may be confused here about this minus sign. What does it mean? Well, remember, potential is a scalar. So the more negative it becomes, the less it becomes, and vice versa. So negative 30, for example, is less than negative 15. And the value of the potential at infinity, where r is very, very high, can be taken to be 0 by convention. That's how the r comes in. We should always have an idea how these formulas have been derived and the arguments behind them, although I've not done that here. But the answer is negative 1.18 times 10 to the 7 joules per kilogram. That's the potential at a height of 2.5 times 10 to the 5 metres above the surface of Mars. Question 4b. Now in question 4a, we were speaking about gravitational potentials at a point above a planet's surface. Now in question 4b, we're speaking about gravitational potential energies of space vehicles of known mass placed at that point. Now, the mass of our vehicle is 4.3 times 10 to the 3 kilograms. So to find its potential energy at a given gravitational potential, just multiply the potential by the mass and you've got its potential energy, its gravitational potential energy. Remember, joules per kilogram times kilogram gives you joules. Now we're asked to find its change in potential energy as it goes from the lower to the higher potential. The higher potential, this being negative 1.10 times 10 to the 7 joules per kilogram, that is greater than negative 1.18 times 10 to the 7 joules per kilogram because it's less negative. Find the difference between these two gravitational potentials, multiply that by the mass of the vehicle, and you've got the changing gravitational potential energy of the vehicle as it moves from the lower to the higher gravitational potential. Question 4c part 1. Calculate the escape velocity for planet Mars. Well, if you look at the relationship sheet, we've got a formula. Escape velocity is equal to the square root of 2gm over r. In this particular case, the r is the radius of Mars, and it's just the radius we need here, because we're assuming the thing that's leaving Mars is on the surface of Mars to begin with. M is the mass of Mars. Put all your values in, and then you have an answer of slightly more than 5 kilometers per second. Where did that formula came from? Because it's always a good idea to know this, even though you might not be specifically asked. Well, it's basically an energy change problem. As the vehicle is rising, its kinetic energy is being changed to potential energy. And the interesting thing here is, when our body is at infinity, it's got zero potential energy and it's got zero kinetic energy. So zero potential plus zero kinetic is equal to zero. And that's exactly the amount of energy it had to have as it's leaving the surface of the planet. Now, the surface of the planet, it starts off with a potential energy, which is negative. Now, the kinetic energy that the body must have as it's leaving the surface of Mars must be numerically equal to its potential energy. And if it's numerically equal to it, then when you add them both together, they're going to get zero, because remember, potential energy is negative. Then solve it for V and you get your escape velocity, square root 2gm over r. Now you might be wondering, how can it have zero energy on Mars and zero energy at infinity? Well, remember, zero is just a number. And its total energy at all points in the journey as it's leaving Mars to get to infinity is always zero. That's its total energy, kinetic plus potential. Question 4c part 2. Recall, the escape velocity for a planet was worked out for a vehicle leaving the surface of that planet and going all the way to infinity outside that planet's influence. Now we're at a height of 5 times 10 to the 5 meters above the surface of Mars, and we're in orbit, so we still experience Mars's gravitational pull. Therefore we are not at infinity, therefore we do not have to leave the surface of Mars with a velocity equal to that planet's escape velocity. Question 4c part 3. Now we're asked to work out the tangential velocity of a vehicle in meters per second as it orbits Mars. Now we use a force argument, and not an energy argument here, it's a force argument. Recall, anything moving in a circle, or going around a circle, as mentioned before, question 2, has to have an unbalanced force acting on it. And the magnitude of that unbalanced force has to be equal to mv squared over r. Now the only force acting here is the gravitational force. In this case, the gravitational force is the centripetal force. And that's equal to big G, big M, little m divided by r squared, where big M is the mass of the planet and little m is the mass of the vehicle. So we equate these things together, the mv squared over r and the force, because they're both the same thing. Solve it for v and you get v is equal to the square root of big G, big M divided by r. So it doesn't depend on the mass of the vehicle, the velocity, as is often the case. Put your values in and you get 3.3 times 10 to the 3 metres per second, or 3.3 kilometres per second. And that's the speed of a vehicle at that height above the surface of Mars, and it will be the same for all vehicles at that height, irrespective of their mass.